We weren't able to ever really find this, so we just went ahead and did it, and did a direct comparison of the exact same part from conception to pricing. So in order to do this, there is way too much inside of manufacturing in order to take something like a generic toy, because there's way too many factors within that. So we started with something very simple, a cube. A theoretical client wants to come to us and they want to make a brick, a 50 millimeter brick. And they want to know what it would cost to do with injection molding or with 3D printing. Well, first of all, we tell them you have to design for the end process, because putting a square peg into a round hole will not work. If you have an injection molded design, it should not be 3D printed. If you have a 3D printed design, it should not be injection molded. And whatever process you decide to use in mass production, you should design towards. But since it's a cube, it's a fairly simple matter to show the two different options. If you are making an injection molded cube, the first thing you have to do is apply a draft angle. So you have to apply at least a 1.5 degree angle to the side of the cubes. It's no longer a cube now, but at least it can be removed from the mold. After that, you cannot have a solid brick or a large mass of plastic anywhere within inside an injection mold. Otherwise, it'll shrink and cause all sorts of problems with the final part. So you actually have to remove the entire center of the cube, removing an entire face so that a cavity can be made. We made the thin walls 2 millimeters thick in order to have it be a nice rigid functional part, because this cube is going to be used as an end cap for a fence post or something like that. So we removed that. And now the cube is no longer a cube, it's more of like a dish with one wall missing and thin walls throughout, but it is injection moldable now. And then of course you want to go around and you want to fillet every single sharp edge, because sharp edges do not exist in the real world. For the 3D printed version of this cube, all you have to do is take the design of the cube and fillet all the edges. There are a few other tricks that can be applied too, but they are tricks and small optimizations and are not necessary to print it. This is a fully solid cube that is now ready to 3D print. So much less design consideration for this particular part. Doesn't apply always, but in this case it does. All right, so we have two designs fully optimized for the process that they are intended for. So what we did is we went ahead and we took the injection molded cube and we had it quoted by an injection molder. We are not going to mention the name of this injection molder, but it is a name that you would recognize, and it is not the cheapest option, nor is it the most expensive option. We selected draft quality, the material was PLA, and we requested a 30-day lead time for this project. And then we sent it off to be quoted. It took about 2 days to come back. We did the exact same thing on the Slant 3D website, the way any client would who's coming to us. We had it requested for 10,000 units, a 30-day lead time, out of PLA, and mentioned that it is a draft quality part which is meant to be on top of a fence post somewhere. It needs to be functional, but it does not need to be super pretty and does not have a glass smooth finish. The quotes come back in about 1 to 2 days. That is the same for Slant 3D, and it was the same for the injection molder that we worked with. And here is the total cost of the parts. For the injection molded version of the part, the cost per piece was $1.42. That is with the injection mold cost itself included in the cost of per part, and it was going to continue to decrease as it went up, but it was flatlining around about $1 per part as you got into towards about 100,000. The 3D printed version of the part, quoted by Slant 3D, cost $1.55 per part. So you know we didn't cheat, because we were more expensive than injection molding. But that is a pure per part cost for 10,000 units. Again, a bit more expensive than injection molding, but not extravagant. And you have to consider the whole rest of the supply chain whenever making the consideration. The part cost alone is not the only thing to look at. For fun, we also looked at 500 units just to show how 3D printing helps at lower volumes. At 500 units, the cost per part was $13, again because you still have the cost of the mold right off the bat. And the cost of the mold in this case for the simple cube was $5,700. Which is not a small amount, especially since that's what you have to pay in order to get your first part. Whereas the cost per part for 500 units with 3D printing was $5.12 a piece, which obviously is much less than the molding cost because you do not have the mold. And this is not something we generally want to highlight because we don't believe that 3D printing is a small scale production method. It is most certainly better than molding at small scales, but it is very clearly as good as injection molding up to production scales. Toyota considers 25,000 units to be mass production. So if we hit that, we are at the same manufacturing level as one of the best manufacturers on the planet. Very, very few products ever make more than 100,000 units in their entire lifetime, let alone between iterations. And this is something that has to be considered with molds too. What if the product comes out of the mold is not what you expect or not what you wanted? The cost to change the design is $5,700 every time, if not more, depending on how complex your design is. Whereas the cost for 3D printing is $150. That is the setup cost to start up production of a production run of parts. Lead time between the two was identical, but one of the bigger differences between these two also was the location the parts were made. The parts in this case would have been produced within Boise, Idaho in our main mega farm facility. The parts from the molder would have been produced in China, which means that after they are produced, they then have to cross an ocean, go through customs, be delivered at a warehouse, and then distributed to wherever the final product is going. Whereas with the 3D printed parts, they can be produced here and shipped to your main warehouse within the continental US, or they could be fulfilled one at a time from our warehouses. So you have much fewer steps in the supply chain with much lower cost. And while these two projects were quoted side by side, 30 days and 30 days, that is the wrong way to use 3D printing. If you were making 10,000 parts and these were to be used for the entire year, there is no reason to order 10,000 parts. You would go into a contract with us for 10,000 parts, but we would produce 1,000 parts per month and deliver them to you. This would reduce the amount of warehousing that you need to hold those pieces. And if you need to make changes based on customer feedback, you can do it in between batches rather than having to buy a $6,000 mold every time you make a modification to the parts. So ultimately, this is what we wanted to do. The two quotes are linked down below for folks to reference if you want to look at them. But what we wanted to do was just show a very simple part side by side with injection molding and 3D printing with very hard numbers from both organizations to make sure they can be compared side by side. Now, this is just an example. Whatever your part is can radically change how these dynamics work out. But this is simply a way of showing that you should be considering multiple processes whenever you manufacture your product. And hopefully this showed some new information about how to design a supply chain around 3D printing and how the supply chain around injection molding works. Let us know down in the comments if there's other topics that you'd like us to cover and other components of mass production 3D printing that you haven't really heard much about before. Have a great day, everybody.